Let's do a quick review of a couple of things. Very basic stuff. Voltage is the potential difference, this potential energy that electrons have as we apply a potential difference, and we force electrons to move from one side to the other. Just a quick revision, electrons will always flow from negative to positive, but because we didn't know the atom and we didn't know flow was in one direction versus the other, we're actually going the opposite way. We're going to say that current flows from the positive voltage to the negative, and the symbol that we use is a straight line like this and a small line like this. Do double for a large cell voltage. Doesn't really matter though. The idea though is that the part where there's a short line is the negative side, and the part where there's the longer line on top is the positive side. So if I were to draw a circuit like this, current is flowing in this direction. This guy here is a symbol for a resistor. Another symbol for a resistor is just a rectangle, but I tend to draw the squiggly line because I like the historic significance behind it. I honestly found conventional current flowing opposite to the direction of move harder to get to my head around than wave-particle duality. Sometimes it can break your brain for sure. Oh, that's not that great in the end, Hacks, is it? I might be spouting nonsense that Ireland's severance package is that great. Well, it's not so much as accurate. I'd say the rectangular ones is more accurate to more modern structure, but I just like the historic significance to the squiggly one. Rabbit hole. What's the funny story about this? That's how resistors used to be made. It used to be a copper wire, and you would make it super, super, super long and squiggly, so it's more compact and takes up a whole lot of space, and because it's a very, very long wire, it ends up having a lot of resistance, and that's how resistors were made. So that's where the squiggly line came from originally. It's a very, very long wire in there. Excuse me, I'm burping. Hi Harold, welcome in, welcome in. Alright, so we have the symbol for voltage, we have the symbol for current, and we have the symbol for resistance. Now, when we solve problems, one of the most important things to always remember is that Ohm's law is the thing that governs the universe. Voltage is equal to current times resistance. This is going to be our bread and butter. Almost everything and anything that we're going to solve comes back to this, okay? So the idea is that as you increase voltage, you increase current across a constant resistor. If you plot voltage versus current, you actually get the value of that resistance. I've done this experiment before. Maybe once or twice, maybe once on the front page, but we're just gonna kind of skip over it, accept that to be true. When you have several resistors in a circuit, you can just add them in series. Resistor total is equal to resistor 1 plus resistor 2. But a little odd thing happens when you have a circuit and you have two paths where current can flow. This is a symbol for ground. You can assume I've closed the circuit here. When current has options, the total resistance in a circuit changes. Think of current as water flow. So now at this junction right here, water, i.e. current, has options. We've given it a choice. And so obviously current isn't a conscious thing. It isn't like a thing that has consciousness and choice in the sense that it chooses one of to flow in this path more than the other, but rather the resistance that's in place kind of logically dictates where current is going to flow. I always say it is like going grocery shopping and you're at the checkout aisle and you see that there is an old couple and another older couple with loads and loads of shopping trying to get through. And there's another aisle and it's just one fella with a couple of beers going through. All right. Where are you going to line up? You're obviously going to line up behind the guy with the beers because, you know, chances are it's going to flow faster and a lot more of you, humans, will flow through that checkout way, way faster than the one with the elderly couple. And so that's kind of the idea of resistance and where current tends to choose. We're the checkout people in the aisle and we tend to choose one of the checkouts over the other, but it's not really a choice. It's the one that's flowing faster. There's logic behind it. We move towards that line to get from one side to the other. All right. And obviously, if you're a weirdo, you might, you know, go to the slower checkout if you wanted. You know, I don't know, just wait. Knowing my luck, the guy spends 20 minutes trying to chat up the checkout offer. Exactly. Obviously, in real life, anything can happen. Shit happens, right? Now, when current has choice, how do we calculate the total resistance in the circuit? Well, the formula becomes ever so slightly different. It's the inverse relationship. 1 over RT is equal to 1 over R1 plus 1 over R2 in this specific case. Yeah, it's Expedition 33 soundtrack. If it gets too distracting, let me know. Hi, Chingmania. Is an ageist. Oh, goodness. The idea behind it is that current is going to flow in the path of least resistance. Kind of makes sense. It's kind of like lightning. Lightning always finds a path of least resistance. I always find it odd, slightly, when people argue and say that lightning never strikes twice in the same place. I understand why they say that. Actually, I don't know if people understand why they say that, now that I think about it. Why do you say that lightning doesn't strike twice in the same place? Well, it strikes that place because there is a point charge, copper rods usually, or there is a huge buildup of the opposite charge on the other side. From the clouds, there's the other charge. It becomes overwhelming. Lightning strikes. Happens. But the minute that lightning strikes, it dispels that charge. However, if it dispels that charge, or how did it even build that charge in the first place, consequently probably means that lightning is going to strike in that area again. Again, it's a lukewarm argument. Just bear in mind that I hate that figure of speech because it's not very true, I think. I go to self-checkout. Same. Hi, Igor. Welcome in. All right. I think that's relatively okay-ish description of everything we need to know. You can, Kirchhoff's law and voltage law is the sum of all the voltage drops equals the total voltage source. Energy cannot be created or destroyed is the fancier or the less fancier version of that explanation. And finally, the current is the same at any given point in a closed series circuits. That means that the current here is the same as the current here. It's not the same here. The current splits, but it joins back up together. So this is just a quick crash course revision of Kirchhoff's laws, resistors, and circuit ideas. And how about very old friends? Hi, Silver. 26 months. Thank you so much for the resub. Really, really appreciate it. Thank you. Hi, John. Hi, Ad, by the way. I hope maybe by the end of today to get there, Sour. We're just starting at the introduction level. But yeah, maybe we'll get to Norton Thevna. I definitely want to do principle of superposition though. And branch theory or loop theory. Hi, spray. And there it is. Thank you, Silver, for the resub. Alright. We'll just move this slide here. Damn it! This is why you should clean your board after yourself. I believe. Hi, Medjay. How are you today? Nice. Well done. Nicely done, chat. Just have to wait a few seconds to, let it dry, unfortunately. Hi, Handalorian. Welcome in. Hi, Mike. You've watched every episode of Big Bang Theory. I don't know if it's a very accurate depiction of physicists, but you're more than welcome to hang out here. We're just doing a bit of circuit analysis theory today. And that looked like you were working the Yeah, exactly. I was doing the derivation for RMS, root mean square, because a lot of people know, well, some people know that the root mean square is 0.707 of VP, but nobody knows where that came from. So I did the calculus. Yeah, I did the calculus, the integration of the average of half a wave over the length, then square it and then root it, i.e. root mean square. Maybe I'll make a post this week on the average, because people might not know that as well. I love that cup. Thanks, Bubster. Drive faster. The holy square root 2. Yeah, because average is 0.6 something. Forget now. Oh, it's pi over 2 of VP, isn't it? Or 2 over pi. It's 2 over pi, chat. 2 over 3.1. That's 0.6 something. Oh no, you have a cold. Jesus Christ, Jay. Back-to-back sickness. You poor... That's insane. You've a cold too, Nexus? Aw, lads. Did I get sick this year? It was before... When did I get sick? I was sick recently enough. Must have been ages. No, it wasn't. It was on stream. I remember. I got sick on stream. Damn it, I don't remember. Anyways, it was what it was. Clearly, I got you all sick via online. No, just Twitch, Instagram, TikTok. Those are my only socials that I'm on. Wash your hands, don't be sick. Very, very good advice there, perfectly stiff. Okay, I think my board is dry. Let's actually solve a complicated circuit. Or a first introduction to a complicated circuit. Ta-da! Okay. And let me say that the voltage is 5 volts, 47 ohm, 32, and 50 ohm. There we go. So my question will be, number 1, what is the total resistance of the circuit? Number 2, what is the total current of the circuit? And number 3, what is the current across resistor 1 and resistor 2? And what are the voltage drops across all resistors? There we go. Those are loads of questions that we need to solve, but honestly, it'll be a great practice. You'll solve a lot of things. What you're going to notice that all you need to know is have a couple of brain cells on energy cannot be created or destroyed, and Ohm's law. And the reason I love teaching this, I know a lot of people are going to jump in and say, but you can just use Kirchhoff's voltage law, but you can just use the current divider equation, but you can just use the voltage divider equation. And it's fantastic if you know that. That's great. Why I like to teach this very, very slowly and painfully and pedantically is because, especially in the first 2 years of electronic engineers and physicists and so on, anyone who kind of does these modules, is that people lose sight of what voltage is, especially when you do voltage nodes and things like that. People lose sight of what current truly is. And when you kind of have these kind of circuits and concepts, they race on ahead to solve it and make such very basic mistakes from Ohm's law, but also just from like energy cannot be created or destroyed, but can only transform from one form or another, all these kind of ideas. And it just goes out the window because they do this in such a purely mathematical way that that's something, how should I say this? The mistake would have been way, way easier spotted had you used common sense, if that makes sense. Again, I don't mean common sense in a mean way, like you don't have common sense to solve it. What I mean by common sense is just understanding how voltage works and why it does the things that it does, and why current flows the way it does, different paths and so on and so forth. If you keep track of those, after that, let's assume that that is common sense, then all of this is solvable. Oh no, a couple of brain cells, that's me out. Kind of, I would say it is physics common sense, exactly. Sometimes when we solve these circuits, we dissociate a little bit. Because it's just mathematics, and you forget the physics behind it. Okay, first steps, let's solve what the total resistance in our circuit is. So we know that if it's in series, we add them all together, but the problem is these two guys, they're not in series, they're in parallel and then in series with the 50 ohms. So what we need to do is we need to do an equivalent resistor. It's basically, we make up an imaginary resistor and we solve these two guys in parallel first. Now, there's a way to do this way, way quicker, but we're just doing this slowly, step by step. So, one of the equations I told you is this one for parallel. You can do the maths out, you can multiply them across, but trust me when I say this, it's the same thing as this. And the reason we use it is just, it's way, way, way handier, way, way quicker because you don't need to invert it. And again, just from experience when I teach this, students tend to forget to flip this guy upside down in the end. They'll do 1 over R1 plus 1 over R2 and they forget to flip it, unfortunately. And good mental maths for you is that your equivalent resistor is always going to be smaller than your smallest resistor in your parallel. So when we're going to do this maths, we know that it's meant to be less than 32. It has to be, okay? So we can do that mental math really quickly if you want, but let's add these two guys together. 32 multiplied by 47 all over 32 plus 47. Did anyone do the calculation? I think loads of people in the chat wrote stuff. I'm so sorry, you guys all wrote stuff earlier, but I didn't see the answers. 19, thank you, 19 ohms, perfect. And I know that that's roughly right. I can tell you that that's roughly right because it is less than 32, okay? Small mental maths to do in your head. If both resistors were 100, right, R1 and R2, your equivalent resistor would be 50. Just to kind of have a mental mathematics behind it in your head. So 19 ohms sounds very, very reasonable. So we have an equivalent resistor of 19 ohms in series with 50 ohms, like this. So you add them together and lo and behold, I did see the answer earlier. Would you look at that? We got a total resistance of 69 ohms. How about that? Nice. Yes, yes. Exactly, Sarah. Exactly, Nightshade. Welcome in, guys. Dirty ohms. Coincidence? Yeah, it is a coincidence. Do you know what? My students never laugh at 69. Anytime the answer is 69. Conrad, thank you so much for the resub. Really, really appreciate it. Did you have fun playing with other scientists? I did. I did enjoy talking to students for sure, yeah. And I got to meet a few cool physicists at the conference. It was good. It was good. Yeah. The new generation, they all, if it's 67, if it's 67, they would have lost their minds. But they don't laugh at 69 anymore. That's the new generation. Yeah. Are you a professor or a PhD? Neither and both. So I have a PhD, but I'm not a PhD student. I'm a lecturer. In Ireland, professorship is different. I know in some parts of the world, if you're a lecturer, you are a professor. In Ireland, professorship is different. I think they're changing it this year or next year. They're kind of changing it a little bit now. But yeah, professorship is a different thing here. No, let me clean it first. I'm going to make the same mistake again. Throwing your teacher. Oh, shit. I didn't submit the funding. Remembered something. Okay, it's fine. It's fine. What date is today? Oh, it's only 1st of March. It's fine. Sorry. Don't mind me. I'm trying to dissociate a little bit from my emails because I've been replying to emails on weekends. And that's not healthy, you know. So I'm trying to be better now. Trying to take weekends seriously. Oh, goodness. Yeah, stop. No, you're right. It's just, it's really hard in academia. You're expected to work all the time. It's an unwritten rule. But I've turned off the notifications off my phone, so I don't get email notifications anymore when I'm at work or on the weekend. Sorry, I'm just waiting for the board to dry. Apologies, my whiteboard is just terrible. Where are you from? Ireland. So in Ireland, professorship is like a thing that you have to apply for. There's only a limited amount available every year in the whole country. You need to submit some remarkable thing. Even something called a senior lectureship is also limited. Basically, you have to wait for a senior lecturer to die before you could get a senior lecturer position. And you have to apply for it. Crazy, isn't it? Use the dry side. Yes. I think this side is dry now. You're right. Okay. You could try to expedite the process. Hi, Fixola. Welcome in from France. Lab incidences do occur. That is true. Oh shit, why did I rub that off? Oh, lads. Okay. Let me draw it again. Damn it. Oh my god, this is a disaster. Do this. Pat, this is all your fault. You distracted me. $69 ohms, 5 volts, 42, 32, 50. Does anyone remember what the two resistors were again? I think it was 32 and 47 maybe? I think it might have been 47. Happy Saint David's Day to the Welsh viewers. I don't think it was 47, wasn't it? It was 3247. Thank you. Okay. So what we've done is we've redrawn the circuit. Technically, in my circuit, I still have those 3 resistors, but we still get 69 out of it. The total resistance is 69. And so using Ohm's law, we can solve for the total current in a circuit. V is equal to I R. By rearranging the equation V over R, we can get the current. Our voltage is 5 volts, our resistance is 69 ohms, and we get just on less than 100 milliamps, right? 72 milliamps, thank you. We get 72 milliamps. So that is the total current in our circuit. Moving forward, We know that the current is going to go in here, and it's going to split up. Okay, so we have 72 milliamps, 72 milliamps, 72 milliamps, 72 milliamps, 72 milliamps, and then the current splits. Okay, and our question is, well, by how much does it split? Now, we could use the current divider equation. I get it. We know how to do the current divider equation, some of us, but we're not going to use it. Let's think, how do we solve this? Okay, well, we can always use Ohm's law. If we have one of the three things, we can solve it. We know the resistance, 47 ohms. We don't know the current, that's what we're looking for. Could we get the voltage? Interesting question. Let's go back to that circuit we drew when we had the equivalent to resistors. Yeah? So this guy's 50 ohms and that guy was 19 ohms. Let's look at this. When current flows through this, and it's the same current the whole time, in this equivalent circuit, the current always is going to be 72 milliamps, because there's nowhere else for the current to go. The voltage drop here and the voltage drop here has to be added up to 5 volts. Energy cannot be created or destroyed. The sum of these two guys, voltage drops, has to equal to 5 volts. But how can I calculate the voltage drop across each resistor? V is equal to IR. We know the current, we know the value of the resistance, we can calculate the voltage drop for each guy. So the voltage drop across the first equivalent resistor is going to be 72 milliamps multiplied by 19 ohms. So that's going to be roughly 1.4 volts? Is it 1. Does anyone know? Could anyone put that in their calculators for me? Sorry. 72 multiplied by 19. 72 milliamps. 72 by 10 to the minus 3 multiplied by 19. Hi Bulbadim, how are you keeping? I think it's roughly 1.4 volts, but I could be wrong. $1.368, excellent. Thank you so much. 1.37, we'll round it up. Very good, very good. 1.37 volts. Now, I could do the maths again. V is equal to IR. V is equal to 50 ohms multiplied by 72 milliamps. But I could be cheeky. I could be very lazily efficient. And I know my laws of physics. We know that 5 volts is the total. We know that we lost 1.37 here. So 5 volts minus 1.37. Our voltage drop across resistor 3 is going to be 3.63 volts. Exactly. Well done, chat. You all figured it out. Very, very good. Very, very good. Now, why did I spend all that time on that? Well, let's go back to this idea that we're trying to solve how much current is going this way and how much current is this way. We calculated what the voltage drop. The voltage drop across resistors in parallel is the same. So if there's 2 volts being dropped here, 2 volts have to be dropped here. If you want, after this, I'm actually going to show you a potential divider thing. I'm going to show you when you load a potential divider, no matter what, the voltage is going to be the same in parallel. I'll do a little demo. Don't worry. I'll come back to that in a second. I'll prove this concept to you physically, so you guys can believe me. Where was I? Yes, so we know that 1.37 volts is dropped here. So V over R, the voltage is 1.37 and the resistance is 47 ohms. So that's going to be the current that goes in this path. We'll say I1 and this is I2. And so the current going through I2 is V over R. The voltage is the same, 1.37, but it's going to be the other resistor value, 32 ohms. But what about wire resistance? Listen, the same as air resistance, wire resistance doesn't exist, Gov. We should know this by now. Exactly, Durloy. I appreciate the chiming in. So 1.37 volts divided by 47 ohms, that will be the current for the path in this first resistor. And 1.37 volts divided by 32 ohms is going to be in this direction. And you can kind of see that the smaller the resistor, the more current that's going to flow through it. Ohm's law still holds true. The perfectly canonical penguins. Thank you, Sarah. Appreciate that. So you got 0.03 amps for this one. And 0.04 amps. And the total thing is 72 milliamps. It adds to 70 milliamps. I know there's a decimal place. But yeah. It does add up excellent. Brilliantly. So we were able to calculate the total resistance of our circuit. We are able to calculate the total current in a circuit. And we even knew where the voltage drops happened and where the current flow, all just using Ohm's law. We didn't need the potential divider equation, which also comes from Ohm's law. And we didn't need the current divider equation, which also comes from Ohm's law. We didn't need any of those equations. We could just solve it pedantically and painfully using Ohm's law. If you have Ohm's law, you can solve any DC circuit theory. I'm going to eat those words. Listen, don't talk to me about diodes or transistors. I'm just talking about everything else. How much circuit theory is in university level physics? It depends what course you do. So my bachelor course, I didn't do proper circuit theory. Yeah, it was assumed we knew it. In the one I teach now, we do DC AC circuit analysis theory. They do one module on it. So it just depends on your course. I feel like if you're doing an applied physics course, you should be covering this. Yeah, very important. It is fully proportional. Yes, it is, Mata. Welcome in, Chisholm. Even mathematically, you can take to it, Happy Pepperoni, you would need to take into consideration energy lost due to friction. There's the issue of gravity. There's the issue of air resistance, heat dissipation, all those little things. Even mathematically, you could do those. Now, I'm going to show you that this is true. So something I said earlier is that the voltage the voltage is the same in parallel, and I'm going to show you that. Actually, let me clean the board first because I'm always waiting for it to dry. So we're going to clean it. I'm going to get a board. We're going to show this through. Yes. 3 sets of resistors here. Some wires. I'm coming. Quit nagging me. But air resistance doesn't exist. Listen. Air resistance exists when tofu says it does. Hi, Effentriel. Welcome in. Okay.
You have done nothing but lied. You
are a liar. You are a self-confessed liar. You know what? Fair enough. I'll accept that. Ugh. How you doing? I'm doing good. How are you keeping? I'm a bit tired today, just because of the 2 long day conference. But honestly, it was good fun. It was good crack. I met loads of new friends, actually. Got to meet some really cool social media people, which was awesome as well. Know how it should flow, because it's not till the wave returns. It is so instantaneous, Rabin. It is extremely instantaneous. I know that, Veritasium made a video and a lot of people like to highlight this. But when you're talking about DC circuit analysis and anything that we're building here, it's instantaneous. We have to be careful about that word. I think that a lot of misconceptions happen because of that. Where when we say, how does it know where to flow? It's I'm a culprit for this, but we need to be careful when we say things like that in physics. Current doesn't know where it wants to go. Voltage doesn't know where it wants to go. I use this language all the time. It doesn't have consciousness. It literally is the situation of the universe that you put it to. You drop a ball, it falls. You don't ask the ball, how does it know to fall? It just does, because that's the laws of gravity and the laws of physics being enforced upon it. Well, again, that's probably a wrong language again. It takes the path of least resistance, least amount of obstacles. It just, do you know what? It all goes back to entropy, and it all goes back to, what's that law again? Oh, for feck's sakes. Do you know the one that has a weird... What is it? Not path of least resistance. It's the fancy version of path of least resistance. Path of least action. Thank you. There's another term for it, but I know path of least action is another proper term as well. Ugh. Sorry, I'm turning on my power supply. Have you studied network analysis and synthesis? No, I have not. Do you do electronics projects or just theory? Most of the time I build stuff on stream, and it's usually electronics and stuff, yes. But today I just lost my soldering iron. I left it at work, and so I'm not doing the project today, so we're just doing theory today instead. Well, I say theory, but we're going to do a demo. I'm setting up a circuit now. We're going to do actual stuff here, like Tony Stark. I wish I was like Tony Stark. Do I actually? Maybe I don't want to be that. Never mind. That whole billionaire thing makes me uncomfortable. No soldier left behind. Let me bend you guys over. You guys can see what I'm doing. Zoom in a little bit. Sounds like an excuse to get a second. I would love, do you know what? I would love to buy a second soldering station, and I will buy a more expensive one if I have to. But it'd be great to get a sponsorship instead, you know? We've had some cool sponsorships recently. So, don't mind me, I'm just shorting my... I hate this power supply, it scares the shit out of me. But I have to set the current limit this way. Okay. Alright, so what I'm going to do is I'm going to just build a very simple circuit for you guys. Let me grab a breadboard. I lost it again. Okay, we have a breadboard. Quick crude revision. Let me get a pencil so you can see this. So these guys are all connected in series in a line. These guys are all connected. Just because it says negative and just because it says positive doesn't mean they're actually negative or positive. The only reason they are is because it's just trying to visually assign them to you. You can do whatever you want with those lines, but just be mindful that this drawing means nothing. It's just a drawing. A lot of people seem to have a misconception about that there's some positive weird line in place, but that's not the case. Hi, Mort. How are you? It's off camera now. Fair enough. I'm fine. I'm good. I'm tired. I was just saying that I was very busy at the conference this weekend. Quite exhausted. But you know what? It was good fun. It was good fun. Hey, Endless Diaz! 2 years!
Thank you. We don't want any more visitors, well-wishers, or distant relations.
And what about very old friends? You are officially a very old friend. Oh my days. That is class. Thank you so much for the resub and supporting the stream financially. You're very, very kind. Thank you so much for the PP points. Those PP points mean a lot to me these days. Is it best to buy a starter kit for beginner electronics or buy item? I think so, geeks. I think you start off with beginner electronics setups and then you build. And then you build outwards from it. So there's 2 kits I bought. A starter electronics kit and a starter sensor kit. And what you'll learn is that you can build almost anything out of them. And then, oh, there's this one project and I need this one thing. And so you'll buy that one thing and it just kind of builds over time. So start off with a starter project is my advice. Hey, googly eyes, thank you so much for your prime. You're very kind. Thank you. Thank you so much. You guys are very kind to me. Thank you. How much is a kit? Oh, they can cost anywhere from, I think €15 is the one I buy. I gave it last year as a prize to some of my students for the best project. It doesn't cost much, but it's just a nice thing to get, you know? So I'm going to do 2 things. I'm going to put a 220 ohm resistor in parallel with another 220 ohm resistor. I'm going to show you some stuff with this. We'll do it in series first. Whoop, sorry. Oh, if I want my wire to make my own rigid jumper wires, should I search for solid core wire? I know what you're talking about. I think that's okay, but honestly, I fell into a trap before, Jack. I looked for a solid core and it still gave me the threads, you know. It could have been just me being silly or something like that. But yeah, I would say yes, but do be careful. I think I shopped on Amazon. Actually, before I do this, let me show you in series first. Oh, do we know if we hit 100 pp? I think we did, because a few days before that, I saw that we had 99 pp's. I assume we hit 100 pp's. I don't even know where to check. Would it be in earnings? Let me open a tab here. I'm not looking at chat at the moment. Don't do anything too bold. Let me see. Here we go. Oh my goodness. We had 131 pp points last month. So yes, we managed to get the pp points last month. It's one of our lowest, but that's okay because I don't stream as often as I used to, so I get it. I hope over the summer we pick it up again. Okay. And I just need one more wire to ground this. We'll show you some cool stuff. Hi Lucas, how are you doing? Lizard, thank you so much for the prime. Oh, you're so kind. Thank you so much for the prime. Really, really appreciate it. And we have a hype train.
Choo choo.
Sky. Thank you so much for your prime as well. Really, really appreciate it. Choo choo! All aboard the scam train! I should really not have my gain at maximum while I was doing that. Thank you so much. Really, really appreciate it. You guys are coming in a perfect moment. Let me show you this. Show you this. Okay, so I'm going to assign quick maths to my chat. Okay, everybody get your calculators out, pens and papers. I'm going to supply 5 volts to my circuit. And in my circuit, choo-choo-choo, let's follow the train track. Choo-choo-choo-choo-choo-choo-choo-choo. It meets one resistor. And then another resistor straight afterwards. And then back to ground. Okay? The question is, how much voltage is going to be dropped across the first 220 ohm resistor and the second 220 ohm resistor if I supply 5 volts? Now you might be thinking that there's a lot of maths here. It's not too crazy, I promise. I'll give you a moment to try and figure it out. Should be nice and straightforward. I'm about to start. Don't mind me copying the homework. Of course, Lucas. I hope everything is well with you. Thank you so much for stopping by. Exactly, it should be 2.5 volts. If the resistors are the same, the voltage drop across them should be the same. Let's test the theory out. So I'm going to put this voltmeter here. Ooh. Sorry, I just want to make sure that you guys can see this. So let me just prop it up for you. Anything? There we go. So I'm going to set this to, voltage. First steps. That's going to heat up fast. No. There's very little current going through it. You can do some quick maths there if you want. And calculate the current in the circuit. It shouldn't be too bad at all. So we're going to measure voltage. We're going to go into the 20 volt range. All right, so I'm going to measure the voltage drop across both resistors, one before and one after. So here and here, and it should be matching the source, 5 volts. Oh, what's going on here? Hold it. There we go. 4.99 volts. That could be just a rounding error. There could be a few issues. What I'm going to do is I'm going to put my probes right here. There we go. Ugh! God damn it. Trying to measure it via the crocodile clips. God damn it. It's just a really loose connection with my probes. It's just jumping around because I'm probing it incorrectly. Anyways, it doesn't matter. 4.99 volts, roughly 5 volts. We lose a little bit of voltage. What this guy is supplying might not be correct. There's also internal resistance, all the good stuff. So let's measure the voltage across just one resistor. And you always have to measure the voltage across something. It's hidden in the word. Voltage, or sometimes known as voltage potential or potential difference, i.e. potential, it means relative to something. So you always have to measure across something. So let's measure across this. Why is my thingy bouncing around so badly? Oh, lads, what is going on with me here? Sorry. I'm not usually this flimsy. What? Okay, here we go. So we have 2.49 volts here. And... sorry, it's just a bit awkward to get in here. Ooh. This is terrible. Why probe so bad today? They're never this bad usually. What's going on? Feels like a connection issue. 2 seconds. Oh my god, it wasn't in! For feck's sakes, lads. It's all your fault. I wasn't probing the initial junction probe correctly.
They call it a mine.
And they call it a mine.
A mine!
And the other probe is jumping between 2.49 and 2.5. So slight rounding error. Ever so slightly. Afghan, thank you so much for 18 months. Let's go. If I did my maths right, that's 2 Twitch babies and a year and a half. Thank you, Nafkin. You're very, very kind for your PP points. Thank you so much. Yeah, there could be 10% tolerance on the resistors as well, but mostly it's just got to do with the fact that there's just a slight discrepancy between these values. So 2.5 dropped across here and 2.5 dropped across here. All right, so we proved proof of concept of resistors in parallel or in series. Now I'm just going to turn off the power circuit and I'm going to put these two guys in parallel now. I know it looks flimsy and you're like, Tofu, did you actually really measure the true voltage across the circuit? It kind of looked like you just kept measuring it until I read it. But, you know, listen, I promise I'm not lying to you. Wow, the keyboard is changing colors. I know, right? And I learned how to do all the coding for that via the Demon Core project we finished last time. We should go back to Bob. I think over the summer I'm going to build Bob. I really want to repair Bob. It was such a fun gyroscope experiment as well. But I will fix Bob. It does not bash. It has some resistance, but not significant. No, it's just a copper wire. So it's not too much different than adding another resistor, another wire in your circuit. So a tiny bit of resistance, but not notable in 2 decimal places of a voltage measurement. Okay, so once again, we're supplying 5 volts to our circuit. You might notice something funny about the current, but that's okay. We're going to measure the voltage drop across the first resistor. Let's do that. The voltage drop across the first... Oh! 4.98 volts? Okay, well, what's the voltage drop across the other resistor in parallel? 4.98. How is that possible? Tofu just said that the laws of physics can't be disobeyed. If we have potential energy of 5 volts being supplied, we have 2 resistors and they both have 5 volts. 5 plus 5 is 10 volts. Where did that extra voltage come from? It doesn't come from anywhere. There is no extra voltage. Because these resistors are in parallel, their voltage is the same. Their current, however, is going to be different. Basically, the current is going from the power source in here through this red wire, and then it meets these 2 resistors. The potential energy across these 2 resistors is the same. But the path that the current chooses to flow is going to be different depending on the resistance value. Now, what's actually happening is the total current, I think it's about 45 milliamps, just looking at this value here, there's going to be even split. And the reason why the current is going to be even is because this resistor is the same value as this resistor. So again, I hate using this example, but imagine that current has choice. You're in the little shopping center, you have an aisle to choose, and you see a lady with 3 bananas and 2 apples in one aisle and 2 bananas and 3 apples in another aisle. They're both even. Current is going to flow evenly through these 2 resistors. Okay. Are we okay-ish with that concept? Do we trust me now that potential energy is the same in parallel? You might ask me, well, Tofu, I don't trust you. Will you add another resistor in parallel? And I will tell you, yes, chat, I will. Just for you guys, I will add another resistor in parallel. Will it affect our results? No, I have no idea what this is, but I believe you. Good. That's a good way to live your life. Trust me. It's a terrible way to live. Don't trust me. Don't trust anything I say. I don't know what I say half the time. But you'd be a very good lab rat. Oh, feck. I pulled that out. Whoops. Oh, come on, you breadboard. Oh, sorry, let me grab a different. I would love to be a lab rat one day. It's my dream. Excellent. This is the place for lab rats. Our community are called lab rats. So if you stick around and support the stream in whatever way possible, you will become a lab rat.
And they call it a mine.
Hey, Steve. Speaking of lab rats, thank you so much for the resub. Let's go. 6 months. Thank you so much for your support. You're very, very kind. Thank you so much for the PP. Dropped my resistor. Don't worry. Don't mind me. Do you have a 440 ohm resistor? If so, could add that in parallel? No. I have a 100 and a 330 ohm resistor. Well, you briefly become... Well, you get resurrected quite often here. Medjay knows all about that. Medjay has been resurrected many a times as a lab rat. He did come back as a zombie once. Alright, so I added another resistor in parallel. And look at that. Nothing happens. No, it's just my probes. I'm not a very good prober. 4.98. 4.98. And 4.98. The voltage remains the same. Hold your horses though. Our total current when there was only one resistor was 10 milliamps. When we added another resistor in parallel, it became 45 milliamps. And then when I added another resistor in parallel, 68 milliamps. If you add resistors in parallel, you decrease the current. Think about it. If you're thinking about current as water, what you're doing is you're adding extra pipes in parallel. And that makes sense. That means, oh, more water can flow. You're absolutely right. By adding more resistors in parallel, you're reducing the total resistance of your circuit and you are allowing more flow of current, or in this case, water, to occur. What if we add infinite resistors? Great question. We'd get infinite current then. And we will end the universe. Let me pick you up, chat. Have some uppies. Hi, Rocka, welcome in. I'm not going to put away these stuff. I think there's definitely proof of concept here for sure in a little while. So we're gonna do that soon. I'm just gonna keep my setup here, but we're just gonna clean up the cables and put the resistors where they're meant to go, because I do have this horrible habit of just leaving breadboards and then coming back to them months later and being like, there's 10 different resistors here. I don't know their values. Why did I do this? Why didn't I just clean up after myself? And the regret is big. What if I put myself in the loop? Would I increase the resistance at all? That is a very good question. You could have a little bit of fun with that when we talk about potential loads. Do you have a reference for the electronic kit? I don't, but I know exactly what it was. I will find you it right now. For my starter electronics kit. I bought it on Amazon. I will... It's They all look the same. All these starter kits are exactly the same. So this looks completely fine. I don't vouch, as in like I don't have any money. I don't get anything out of this link. I can't even share the link because it's apparently a very long link. Yeah, like I don't know any better, if that makes sense. It looks exactly like the same kit I have. And there's so many kits. They all, honestly, is that kit. Very, very similar to what I have. I should do that though. I should set up maybe an Amazon reference link, but honestly, it's such a pain in the ass. I'd rather maybe even just make a list of all the stuff I own. Honestly, it'll be a great thing to do. I hope ambitiously to have a website this summer, so I'll upload all my schematics for 3D prints, all my coding, everything. Make it possible for you for secondary school teachers to have access to a lot of this educational stuff. That's my hope anyway. Crossing fingers and toes. Tofu.com, exactly. Yeah, I don't know if the affiliate is worth it, John. Honestly, but it'll be nice to still set it up so you guys can get access to the links. Okay, so we've kind of dealt with resistors in series, resistors in parallel. What could we do with that? Or, well, we can make really, really complicated circuits, but we could also be absolute assholes. And one of the things that we could do to ruin our day is that we could add multiple voltage sources in our circuit. So what is Tofu on about? Well, let me show you. Go up, chat. So let's suppose I build this circuit. Closer, a bit better maybe? Yeah. What if I built this circuit? How would we go about solving this? We have two voltage sources, two sources of current, and I'll ask something like, well, tell me, could you calculate for me what the current through the 220 ohm resistor is? So exactly, Jazz, what we're going to do is we're going to use something called the principle of superposition. And if there's any physicists here in our community, something that you might be aware of principle of superposition is when we deal with waves. So when you deal with waves and you have, let's say, one wave coming in like this and another wave coming in like this. I wanted to make sure the angles were correct. If you have two waves coming in like this, what's the outcome wave going to look like? When two waves collide like this or overlap with each other. Flat, exactly. They annihilate each other. And the way you do that is that at any given point, you add the sum of these guys. So if I draw a line here, the sum is going to be 0. If I draw a line here, the sum is going to be 0, and so on and so forth and so on and so forth. This is the principle of superposition in physics, and we can apply the same logic to this. We're basically going to solve one circuit, shut down one voltage source, solve one circuit from its perspective, then do the same to the other story, and then algebraically add them together. That's the idea of how we're going to solve that. And I'm going to do a very cinematic ending to this session. Not ending to the session, but ending to this moment. And this is where we're going to go for our commercial break, i.e. Tofu needs to use the bathroom. And so when we come back, we are going to solve it using the principle. We'll be right back. But I saw a news article that UK's first year thermoplan went online this week. Oh, that's cool. Is that the Jurassic Park theme? Ba-da-bum, ba-da-bum, bum, bum. Yeah, that's what I was humming. I had to think about it. What was I humming? I don't remember what I was humming. Yes, it was. Hi, Science Bush. Welcome in, welcome in. Sorry, it took a while. I got myself a glass of water. I was tempted to get a glass of wine, but number one, it's only 2 o'clock. And number two, I'm actually so tired. I think if I drink wine, I'm going to fall asleep, so we'll stay away from it. We might drink wine when I need to battle as Kratos, you know, and I need a little bit, you know. Not sure yet, but I think this can also be solved using just ohms and Kirchhoff's laws. But it just depends what you mean by that. So principle of superposition is technically just Ohm's law. So that's exactly what we're going to do. We're going to solve this using Ohm's law. It will help us if we used current divider equation now and the voltage divider equation. So we have an option here, chat. Either I solve this using Ohm's law, it's going to be quite painfully long, or I'm going to solve this by showing you the potential divider equation, the current divider equation, and then we'll go back to it. So those are the two options. I think we should painfully suffer through Ohm's law here. It'll be way better in the sense that we're going to suffer together. You know, brethren in arms, charge to war, something, 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 trauma bonding. There we go. Yes, Tuga is nodding their head along. Excellent. I'll accept that then. I'll accept that as the agreement. So, if I were to ask you, well, ladies and gentlemen, please calculate, and labrats and labradoodles, I always forget that part. I'll accidentally do that one day, you know, in a real conference. I'll introduce everyone, welcome in labrats and labradoodles. I'm just going to do that one day and I'm going to facepalm myself and embarrass myself to no end. Anyways, how will we solve this? So when we use the principle of superposition, the first thing that we're going to do is say thank you very much to Young at Heart for subbing. Really appreciate it for the support. Thank you so much for your PP contribution. You're very kind. A whole 6 months of surviving this class, exactly. First thing that we're going to do is we're going to shut off this voltage source. Now, when you shut a voltage source, what do you do with it? Well, you short it. I know that might seem like common sense, but if there was a current source, we would open it. We'll deal with that later. So what I'm going to do is I'm going to short it. So story 1 is the exact same circuit with no voltage here. And let's say I ask you, well, what's the current going through here? Okay? Let's say that that's the question. Could you solve it then? I think you could. You guys are very, very smart. You'll be very able for it. But if you're like, oh my god, I don't even know where to start, do not panic. I will hold your hand through this. So let's solve story 1. I'll call this story 1. Actually, just to make it a bit like notation different, call it story A. Labrats. Yeah, we're doing principle of superposition. That's exactly what we're doing now. So, to calculate the current going through here, let's solve via story 1. Story A. So story A, let's calculate what the total current is first. We can't know what the current is going through here unless we know what the total current is going through here. Actually, wait a second. No, we'll do that. So that's just resistor 1 in series, and then it splits. And 2 resistors split, 470 and 200 ohms, and they close together and they connect back to the other end of the power supply. So it's just resistor 1 plus resistor 2 multiplied by resistor 3 over resistor 2 plus resistor 3. Because these two guys are in parallel with one another. So resistor 1 is 330 ohms plus 470 multiplied by 220 all over 470 plus 220. Okay, so I know that it's going to be roughly just under 500 ohms, but if anyone is amazing and has a calculator ready for me, could you do the maths because I'm super, super lazy? How did you even log in today? What do you mean, science bitch? Oh, wait, you're talking to each other. I think you might have put something wrong in your calculator, Arcane. Bad brackets, yeah, no worries. And this is why it's good to kind of do this in mental maths. I know it's meant to be less than 500. $480, 479. Excellent. Perfect. Beautiful. Beautiful stuff. So it's 479 ohms. So that's what the total circuit.
And they call it a mine.
Total resistance is.
A mine!
Thank you, Science Bish, for gifting a gift sub to Not That Bright. I appreciate that. Thank you. Thank you. Thank you. Thank you so much, Science Bish. You're very, very kind for supporting this channel and supporting wonderful members of the community. Now, where was I? So that's our total resistance. So we can calculate what the total current is then. Our VT, RT is going to be IT, not the IT that you guys think of, obviously. So that's going to be our voltage source is 4 volts divided by 479 ohms. So our total current in this story is I rounded to 480. Fair enough. I'll take that. 480. So 4 volts divided by 480 ohms equals 8 milliamps. Lovely. Good stuff. Good stuff indeed. So that means that our current is going this way. And then it has 2 paths to take. It goes down this way or down this way. Now, a lot of you will jump in and say, Tofu, just use the current divider equation. Just one more equation. But I didn't derive the current divider equation. We are going to be so painful here. So instead, we are going to have to measure the voltage. So we know that there's 4 volts going in. Some voltage is dropped here. Some voltage is dropped there. So how much voltage is dropped across these 2 guys so that we can calculate what the current is going through it. We're doing this painfully. Remember, we are suffering together. So let's calculate what the voltage drops are going across that. So that's 4 volts going in. We have a 330 ohm resistor and then 2 guys in parallel afterwards. Okay. Now these 2 guys in parallel can be redrawn as one resistor. RQ, R1. RQ is equal to the 2 guys in parallel, 470 and 220. So 470 ohms multiplied by 220 ohms, all divided by 470 ohms plus 220 ohms. Okay, so with that on the board, could we extract what the equivalent resistor value is there? Hi, I'm late. Welcome in, Wild. No worries. Sit down, get comfy. We're going to solve all of this together. Alchemist, thank you for telling me that you know how to solve this. Could anyone give me a number, please? Would you ever so kindly give me the REQ equivalent? About 150. Excellent. Thank you very much. Oh, I could have done that actually, meant. Sorry, I remember because we calculated the total. Yeah, anyways, it's fine. It's fine. 150 ohms. So the first guy is 330. And this guy is 150. Now, you calculated earlier for me that the current going in here is 8 milliamps. What's the current going through R1? 8 milliamps. The current going through R equivalent? going to be 8 milliamps again, isn't it? The current has no other path to take in this equivalent circuit. It's going to be 8 milliamps the whole time. So we can calculate the voltage drop across this REQ. That's what we're looking for. REQ, the voltage drop across REQ is equal to the current times the resistance. The current is 8 milliamps multiplied by 150 ohms. So that's going to be 1.2 volts. I'm going to check my maths. Oh no, rush back. I'm sorry. You got about 1.2 volts as well. Okay, perfect. Make sure to check my maths. If you guys get a wrong, different answer to me, shout at me. I don't know how you can shout via Twitch, but you know, it is what it is. So it's about 1.2 volts. So if we move over here, let's look at the circuit again. We know that the voltage drop is 1.2 volts. How much current is being dropped across this? Well, back to Ohm's law. V is equal to IR. We're looking for I. The voltage drop across resistor 2 over resistance R2 is equal to the current across R2. V2 is 1.2 volts. The resistance is 220 ohms. In your calculators, 1.2 divided by 220 ohms. We're almost done. Well, actually, it's a lie. We're only done half. We're as of this point here, we've done half the maths. Thank you very much. So 5 milliamps, yeah? 5.45 milliamps. 5.45 milliamps. Ta-da! And that is our current. Going through resistor 2 of value 220 ohms when the 6 volt is shut off. We have finished story 1, story A. We are now going to solve story B. Dun 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 dun! Story B is when we have our voltage source here, 6 volts, going through. Sorry, I'm trying to remember what the voltage values, resistor values were. 470. 70, 220, 330. This is story B. Let's leave story A. We've done what we can with story A. Now we're going to solve story B. So rinse and repeat exactly. And our 4 volt source is shorted here. So we're going to do the exact same steps again, but solve the current going through 220 as if the other guy is shut down and only the 6 volt guy is operated. So let's painfully do all the maths. You might say, tofu. We don't need to do one thing, at least mathematically. We calculated the total resistance earlier. You feckin' did not. Don't even go there with me. I'm sorry, I'm getting a bit angry about it. It's not angry, it's just be very careful. Think about it. Now this resistance is in series and these 2 resistors are in parallel. Our total resistance actually changes depending on where we put the voltage source. Be careful. So that's 470 plus 330 multiplied by 220 all over 330 plus 220. Hi Swaz, hi Acer, welcome in, welcome in. So it's 470 in series, and then these 2 guys are in parallel, and that's why we have them mathematically in here. What's the total resistance, Rushback? 132 ohm. This is 132 plus 470 is 603 ohms. Is that right? The total is, I'll keep track of that. This is 132 ohms. Then to calculate the total current, V total over R total is equal to 6 volts over 603 ohms. And you said that you got about 10 milliamps. Oh, 602. Oh yeah, you're right. Why did I say 3? Sorry. Bit of brain lag. There you go. That's okay. No worries. No worries. In story A and now in B, is not the open circuit affecting something? There is no open circuit though. Unless that's connected, by the way. It's not open. It's just not me finishing drawing the lines. There is no open circuit in this part. It's only shorting. So we've shorted the circuits here where the power source was earlier. Okay, so we calculate what the total current is and 10 milliamps, 10 milliamps, 10 milliamps, and then current splits either in this direction or this direction. And we want to know, well, what's the, current going through this guy here. But first, we need to calculate what the voltage drop across those two guys are. So the voltage equivalent is equal to the current, which we calculated 10 milliamps, multiplied by the equivalent resistance. So our current is 10 milliamps, and our equivalent resistor is this guy, multiplied by 132 ohms. We get the answer to be 1.32 volts. Okay, so 1.32 volts is the voltage drop across these two guys in parallel. So I'm running out of space. So I hope you just remember this part of the board. If you ever lose track of it, you can always watch the video back. I'm going to keep the main circuit up still. Let it dry for a second, sorry. My whiteboard needs a bit of water. I captured it in my 36 IQ brain. Oh no. Oh no, no. Sip of water. Oh Jesus, we have some really low IQ people today. You poor creators. I'm honored that you are in my presence today, chat. Oh, Jesus Christ, it keeps getting worse and worse. Okay. Let's look at this. So our voltage is 101.32 in that story. In story B, we're continuing story B here. So the voltage drop across the 220 ohm voltage drop across V2 over R2 is equal to the current going through I2 is 1.32 divided by 220 ohms. Does anyone have the current for that? 1.32 divided by 220 ohms. Last one due to a lecture. You know what? I get that. Sometimes I go to a lecture and I feel like my IQ dropped significantly after that lecture. Welcome in, Prince from India. 6 milliamps. Thank you very much. 6 milliamps. There we go, chat. We solved what happened in story A when we shut down this guy, when we short it. We calculated what the current is when we shut down this guy, story B. And the whole idea, the principle, where the idea comes of principle of superposition, is that we'll algebraically add them. And just be careful, just in case you think mathematically, is there a minus sign, is there a plus sign? Think logically. Let's look at the circuit. The current is going in this loop, from positive to negative. And the current in this guy is going in this loop, from positive to negative. So these two currents There's current flowing, and they join forces together. So you're going to add those two currents. So it's going to be 6 milliamps from story B plus 5.45 from story A. We'll say 5.5, we're rounding up. So our total current after the principle of superposition is 11.5 milliamps. And that, boys and girls, ladies and gentlemen, lab rats and labradoodles and everything in between, is how you solve current or problem solving when you have two voltage sources in a circuit using the principle of superposition. There are handier ways of doing this using node analysis, mesh theory, branch theory, loop theory. But I like to teach this because it's so important when you get to AC. Because when you get to AC circuit analysis, it gets too difficult. Principle of superposition is going to be your best friend. Although painfully slower, it's methodical, careful, analytical, and you can't make a mistake with logic. Exactly as here. If the voltage sources were different, we'd have to solve the circuit a little bit. But you just need to keep track in what direction it's going. So if it was going the other way, you would subtract it. Two current flows opposing each other will be the difference between them. Exactly zero. You just subtract them. Hopefully no blue smoke. Okay. So another problem that I'd love to solve is to show you what happens when there's a current source. So that's another thing to solve, but I'm just going to sit down for a few minutes. That's okay, just to rest my feet. Usually in a lecture I walk around, but because I'm not walking around in my bedroom, not my bedroom, but in this room, my feet kind of get a bit sore. Sitting still is the worst thing, I think, for my feet. For anyone, I guess, but yeah, standing still for ages is a lot. Exactly, Rushback. We're going to do current sources and voltage sources. We're going to mix those two together. What do you teach, Tofu? I teach general physics, thermodynamics, electronic devices and systems, and AC analysis theory. Sleeping on the couch these days, yeah, I don't know. That couch doesn't look too comfortable. Yeah. No, I don't do field theory. My little personal project at the moment is all electronics. I just got really into a lot of projects recently and a lot of it's not even solid state or nanotech. It's not even the physics of technology I'm interested in. I'm really interested in actually like building things these days. I really have a lot of fun with it. In terms of research at the moment, all I'm doing is building contraptions and measurement devices and systems. A lot of fun as well. It's just something that I'm really into at the moment. I like, while I have passion, I'll go where my passion leads me. Science communication is also fun as well. I hope to apply for some minor research in that realm. Just minor research. I don't want to do too much of that kind of stuff because I don't want to take too long of a break from my research in energy grid and electrical systems, battery technology. Just a small break. I'm forced to take a break. I can't do anything about it. I have this weird situation where I became too successful too soon. Basically, it is very rare for a person like myself who finished their PhD to become a lecturer so soon. So there's all these different types of funding in place for early career people, but you can only get early career research funding if you don't have a permanent position. I have a permanent position. I'm looking for early career funding. It doesn't exist. There is no, it's basically somehow, I don't know how this happened, but the funding bodies in Europe and Ireland have only one mindset of how a usual academic career works. And so if you don't fall in that category, you're screwed. And it's the same story. Like if you were like, oh, look, I don't want to be a lecturer. I want to be a researcher all my life. But I think it's like after 5 years of research, there's very little funding for such a late development postdoc as well. So there's just this narrow window of what they think a career in academia is like. And outside of that career window, no funding exists. So basically, I'm forced to take a little break for 1 more year before I can apply for any proper funding. I might as well do stuff. Is there a future? Oh yeah, loads in industry, especially physics. Yeah. I'm into lounging at the moment. It's my current passion. Yeah. So for the first time in the new year, I stopped playing No Man's Sky and I started playing House Flipper. It's a really lovely lounging game to play while you lounge. I'm going to assume Swaz is just that it's this always battle between management versus real people. You know, I saw that as a teacher when I saw the difference between actual teachers and the teaching council and the Irish government. There's such dissociation of what's happening in the classroom. You know, they'll say something like, oh, you can totally manage 35 students in a lab, but then also shove down all these health and safety issues in a lab. And then they expect one teacher to keep an eye on 30 plus students with acids in their hands and then blame the teacher if anything goes wrong. Like, there's all these little things. There's such a disconnect from people who put policies in place versus the people who are actually doing the thing. So I know it feels always like the scientists are fighting the government, but it's not just scientists. It's always the teachers versus the government. For example, something that I know a bit about is renewable energy and renewable energy policies. So many policies put in place are actually not good for the environment and are huge setbacks and enforcing these things. Anyways, yeah. It's just... I would love to see a world of meritocracy be a thing, but I understand the issues with that as well. I don't think any ocracy ever solves any of these problems, to be honest. There will always be problems. So basically, I hate that I'm doing this. I'm complaining, and I'm always going to complain, but I don't actually have a solution. There is no perfect solution, in my opinion. It sucks. I'm sorry. Bad tofu. Hey, Vashi Bunny, welcome in, welcome in. Knack, 5 street, let's go. I'm not a big fan of complaining, though, usually. I'm always a person who's like, if you're going to complain, what's the figure of speech I use? Complaining without providing a solution is just nagging, or something like that. Complaining without providing a solution is just whining. There we go. That's the figure of speech. And I'm a big fan of that, usually. You know, there's no point of you complaining and giving out to someone about how they're doing something if you're not going to offer a solution. What about the best non-perfect solution? Unfortunately, mankind isn't like a physics equation, Conrad. The more I study economics these days, I know it sucks. Oh god, my brain is so much in that basic economics book I'm reading. Even though the author is trying to make economics very black and white to me, the more I study the stories, the more I realize that mankind, economy cannot be predicted. We are such dicks to chaos theory. Because chaos theory talks about how small changes in the early inputs affect the changes on the outputs. And I feel like humankind is even more extraordinary of that than ever before. if that makes sense. Bree Cosplays, thank you so much for the raid. Welcome in, raiders. And I said something really, really blunt and rude there. Welcome in, raiders.
Red alert. All hands stand to battle stations. Lay in an intercept course on the Romulan ship.
Shields up. Load all torpedo bays. Stand by phasers.
Warp factor 8. Engage.
Hello, raiders. Welcome in. Welcome in. How is your stream? You were playing Resident Evil Requiem. Okay, okay. You are more than welcome to talk about how much fun it was, how, you know, interesting it was, and all the good stuff in between. But I kindly ask you, don't spoil it. I want it so badly. Welcome in, welcome in. If you need to raid and dash, we completely understand. But other than that, you guys are more than welcome to hang out here. I'm just checking. Something happened actually to my Twitch just there. My Twitch is going crazy at the moment in terms of followers. I'm not getting the follower notification. We just jumped in almost 10,000 followers in 3 seconds, in 3 minutes. I have a bots in place to protect us from following bots. It doesn't seem to be working at the moment. Ooh. Yeah, I don't know if anyone can see that. I have 26,000 followers at the moment. Jesus fucking Christ, I hope I don't... No, not viewers, followers. Yeah. Absolutely amazing. I haven't beaten it yet. No, I'm glad. I'm glad that you're enjoying it. I can't wait to play Daddy Leon. Oh, it's Grandpa Leon? Is it? I don't know. It depends how old. But yeah, can't wait to play it. It's gonna be so much fun. But yeah, I'm gonna try and wait it out. Need to finish the game that I'm playing at the moment. It's at 30k now. Yeah. Yeah, I think I just got follow botted like crazy. But I hope Twitch will clean it out. I do have root commander and wait, shouldn't I have Seribot? Yeah, Seribot should be blocking them. The good news is it's not coming up in my activity feed. Oh god. It's follow bot stuff. Why do people do that? Oh, thank you for testing good bot. What are you playing at the moment? Kratos. I am playing God of War Ragnarok. There we go. That's the game we're playing at the moment. I don't know how much. We're about halfway through. So yeah. I'm really liking it. It's quite challenging, Brie. It's a difficult enough game for sure. Please accept my real sum amongst the fake follows. Thank you, Blowware. Thank you so much for the 10 months. Really, really appreciate that. It's so stressful though. I hope I don't... Well, luckily. Yeah, anything can happen now. I hope I don't get banned out of nowhere. Do you know, because Twitch has all these automatic bans that happen. I hope it doesn't happen to me now. That'll be very, very sad, especially after Bree raided us and gave us so much support. Jesus, it keeps going. It's at 35k followers now. That's so weird. I've never seen a follow bot like this without the follows on the alert. I might just take a screenshot really quickly. Yeah, I've been follow botted many times before as well. But Seribot usually blocks them immediately, and so is Commander Root. They're really on top of it usually, but it's not being cleaned out. Hopefully everything's okay. We'll cross our fingers and toes anyway. Hopefully it'll be fine. I've been follow botted and I don't even stream. Jesus Christ. That is insane. It's just annoying. It's disruptive. But luckily, at least the alert isn't broken. That's the worst thing that happens sometimes. I'm crossing my eyelashes. Excellent. Excellent. I'm just gonna post a thing about this really quick. Not on socials. I'm just in a crazy thing just happened. Just in the Discord. And it did happen just before you raided, Bree, so you did not bring this trouble in. Although, it would have been nice if you did, because then we could have blamed you. But it wasn't your fault, I promise. Oh, you're on the front page under Legendary Women, so you're right. There's a lot of weird bot harassments that happen. Do you know what? Not that bright. I think you're very bright right now. I think you might have solved it for me. Shh, I have a reputation to maintain. Okay, I just posted it there. Excellent. No, that makes sense. That makes sense. I don't know about follow bots specifically, but I do know that a lot of people who are on the Legendary Women thing, they get targeted quite often with bots. I've never had that happen before. School day and all that. But I really, really appreciate all the other real followers. So I'm very grateful for that. And obviously, don't worry about it. We won't worry about it. Came in here from the front page, which is great. What are we doing? We are doing DC circuit analysis. We built a few things to test some theories. And now we're going to continue with that. We're going to do a bit more principal superposition stuff, if you guys are interested in. But now what we're going to do is we're going to solve the principal of superposition with current sources. So we solved it using voltage sources only. Now we're going to solve it with current sources. Bree, thank you so much for sending your friends over here. I'm really sorry. I got startled by the bot thing that just happened. I want to say a huge thank you for raiding in and sending your community over here. For anyone who is new, I apologize. I usually introduce myself, but I got like a bit flabbergasted there. I'm Tiny Toxic Tofu. I stream science and technology education. Today we're doing DC circuit analysis theory. And then we play video games. But if you guys want to catch someone who does amazing cosplays, amazing playthroughs, she's playing Requiem at the moment. So we're avoiding spoilers. But Bree's playing that if you guys want to. But good night, sleep tight, and make sure the bed bugs bite. Really appreciate the support. Ooh. Press my Discord exit. All right. Now, after all is said and done, let's do some more circuit theory. Sounds like you make puns. Thing is, bots carry a very special technical signature that companies can block very easily. Sadly, they just don't care to implement it. Ah, okay, fair enough. Yeah, no, I hope... Usually Commander Root is really good for that. Commander Root clears all the bots over time. I'm hoping that the 35k followers will go away. We go back to our original 12. Yeah, I think that would be nice. So, let's do that. let's forget about the follower issue and we will continue streaming, having fun. And hopefully we won't get auto banned, because usually that's my biggest scare. I know that if I go through the right channels, eventually I'll get my account back, but I just hate the idea of my account even getting falsely suspended. You know, it's not nice that could happen. Only fake bot followers, all real people. Oh yes. All the other followers, I know there's a few. I can see who the real followers are. I really appreciate. I'm not going to call you out, but I see all of you. Thank you so much. Bloodware, again, thank you so much for the resub. Really appreciate it. See, I see those 2 followers there. Thank you. Let me pick you up, chat. Let me. What? Dropped you. Alrighty then. So, let's do another principal superposition analysis. This time, what happens when one of these bad boys is actually a current source? Let's clean the board first. We finished parallel circuits. We're kind of moving on a little bit, if that makes sense. We've done a lot of those, but we're still going to use parallel theory when solving principle of super. Show you now. Few minutes to dry it out. What toughness of levels of physics do you have to study for a master's in history? I'm so sorry. I did very little amount of organic chemistry. Maybe just 1 or 2 courses or modules when I was a undergrad. I don't remember chemistry. And yeah, sorry. Can't help you there. Apologies, Sai. Apologies about that. And you know, ultimately, it doesn't even matter what I say. If I did experience that, every university around the whole world, and even within their own countries, are going to be very, very different. Stuff like that isn't actually quite not as consistent. That's really cool, Firebrand. I'm glad to hear that. Welcome in, welcome in. We're just waiting for this to dry off, as we're going to try and solve circuit analysis theory. We're going to do principle of superposition, and we're going to show how to solve it if one of our voltage sources is actually a current source instead, and how to do that. And what we've done is we've painfully and slowly not done the potential divider equation, not done the current divider equation. We're doing everything all from Ohm's law. Why? Do not ask me why. It's just why I accidentally ended. It's great. It's a great idea that we can do everything just using Ohm's law, using a little bit of physics, using a little bit of Ohm's law. We can solve anything and everything that our mind. All right. So now, lab rats and labradoodles, what if I draw you this circle? Dun 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 dun! Here's our circuit now. Bam, 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 bam. We have 5-volt voltage. We have a 20 milliamp current source, and we have 120 and 120 ohm resistor set in this kind of system. Looks like a 20. Yeah, so you can actually create something that looks like an ideal current source. It won't be great, but you can set it to look that way. Using transistors. We can go into that another realm if that's interesting to you guys sometime. How can you replicate an ideal current source? We'll have a look at it sometime in a little while. But if we go back to how transistors work and how BJTs work, that's a little hint for you if you're interested down that rabbit hole. Now, here we go. We have a voltage source and we have an ideal current source, and I'm asking you, well, could you tell me what is the current going here? Yeah, exclamation mark Discord is linked to Discord. Well, we're going to do the exact same idea. We're going to have story A and we're going to have story B. So let's look at story A. It says, let's shut down the current source. So we're going to look at it from perspective of the voltage source only. Let's shut down the current source. We're going to do something slightly different. When you shut down a current source, it's not a short, it's an open circuit. So, take care of yourself, Swaz. Thanks a million for stopping by. So what happens is, we have current coming from this voltage source, and you would think logically current splits. But because this is open, it's just basically two dangly wires hanging out like this. That angle. But there's just two dangly wires hanging out like this, and they're not connected. And so there's actually no current at all. And from the perspective of the voltage source, it doesn't even exist. This is what exists from the voltage source's perspective. So we just have a simple current going around from 5 volts to 100 ohms, 220 ohms. This is going to be so nice and handy. Because think about it, I'm just asking you, what is the current going through 220 resistor? Well, that's just this guy and this guy there. It's just one circle, one loop. There is no other current, so it's the total current. V total over resistor total is equal to current total. Our total voltage is 5 volts. Our total resistance is 2 resistors in series. Perfect, there's 320 ohms. So 5 volts divided by 300 ohms should give us the total current, which also includes the current going in this direction as well. So if anyone can have that calculation. Thank you very much. 15.6. Lovely, short and handy. We have solved story A. Excellent. Now, what to do if we're solving story B? Well, in story B, we're shorting the 5 volt source and we're keeping the current source active. So from the perspective of the current, it's going do, and then the path splits. It either goes here or here. The total current here is 20 milliamps, 20 milliamps, 28 milliamps, 20 milliamps, 20 milliamps, and then over here it splits. Now again, if you know your current divider stuff, that's great, but we're not using the current divider or the potential divider. We're being efficiently lazy. And instead, what we're going to do is we're going to calculate, well, what's the voltage drop across this guy? Voltage, distance, calculate what is. Okay? So let's, first step first, let's calculate what the total voltage in a is. So voltage total is equal to current total, and we know the total, and resistance total. We don't know the total resistance. Let's solve that. RT is equal to the first resistor, 200. And then these two guys are in parallel. So that's 100 multiplied by 220 all over 100 plus 220. What is the total resistance? Hi Alex, welcome in, welcome in. I became lost as soon as you came up to the whiteboard. I'm sorry, Chewy. We are in the middle of the lesson, I admit. I'll upload a full YouTube video with the beginner aspects of this in the beginning. Right here. On your calculators, 100 multiplied by 220 divided by 100 plus 220, all in brackets, plus 200. 289 ohms. I know that that's roughly right. It has to be less than 100 ohms, less than 120 must be less than 3. So not too far off for sure. So if there is a mistake, can't be too far. Right, 280 ohms. The total resistance. So let's calculate our total voltage total. You're gonna hate me, chat. We didn't even need to. We could if we wanted to. We didn't need to. If we're looking for the voltage drop across this guy. Oh, no, we do. We don't, but we do. It's fine. The equivalent resistor here, pretend resistor, going to be these two guys together, the parallel one, which is 89 ohms. Our REQ is 89 ohms. Okay? So I'm just going to redraw the circuit here just to see. That's basically what we've done now. Have R1 and REQ. Okay? And our REQ is 89 ohms. We know that in the circuit, our current is 20 milliamps. So the voltage drop across REQ is going to equal to 89 ohms resistor times 20 milliamps the current. So that's going to be 1.78. Did I do that right? No, it's 0.178. Anyone correct me if I'm right on that? 89 multiplied by 20 milliamps? Did I do that right? 0.178 volts? .78. Don't trust myself. Okay, so it's 1.78 volts. That's the voltage drop across REQ, and it's the same for those both resistors. And we're looking for the current that's going through this guy in the middle, and the guy in the middle is 220 ohms. So V over R is equal to the current going through resistor 2. Voltage is 1.78 ohms, and the resistance is 220 ohms. Sorry, 1.78 volts divided by 200 ohms. Our current, I2, in story B, going to be, that rhymed, 1.78 divided by 220. Hi Anchor, welcome in. Sorry, Sai, I didn't catch your message there earlier. Thank you very much. 8.09 1 milliamps? Would that be fair? 8.1 milliamps? 8.1 milliamps. So that's the current going through story 1, and that's the current going through story 2. So 15.6, story 1, plus 8.1 milliamps in story 2. Add those two guys together, that is 23.7 milliamps. That is the total current that goes through our story here. Current going through. And we have one voltage source and one current source in our system. I know it looks like a lot, but when you compare it to when we had two voltage sources, it's actually a lot less equations to you. You do save a lot of time. Now, the other thing that you could save a lot of time for is that if you knew your current divider equation, you knew your voltage divider equation, that could have saved you a whole lot of time as well. So yeah, that can happen, of course. Just to be mindful and wary for yourself. Ooh, down here. Gonna pick you up, chat. Gonna put you down again. Whoa! Sorry, I dropped you guys. My bad. My bad. You guys are okay. Whoa. And that is how you solve principle of superposition by first principles. And by first principles, I mean Ohm's law. Everything is just Ohm's law. It all goes back to Ohm's law. It does make your life easier if you use the current divider for sure. In many of these cases. But even without that, we can solve all of these problems without needing